April. First. So we are going to have a first quiz on April 12th, about 2 weeks from now. It will be about 1 hour quiz. From beginning to whatever we are going to cover next week will be the subject of our first quiz. And preparations. A4, one side. So you can bring one page, A4 size, feeding sheet. In Korean, hunting paper. And handwritten, preferably. But no magnifier. So magnifier is not allowed. I mean, in the past there was one student who made a copy and reduced it, and copy and reduce it. So he needs a magnifier to read his papers. So I would advise you to bring just one page, single sheet, and so you don't have to memorize all the formulas. You can just write it down. And because all the problems are going to be in English, you can bring dictionary. But it's very tricky. You cannot use text. No text, no KakaoTalk, what's the spell of Kakao? I think Kakao. So no line, whatever. So you can actually use your cellular phone or mobile phone for dictionary, right? You have an app, but you cannot communicate with your fellow students using text. It's the honorary system, but my students will check on and off. So if you got caught, then I think you will be expelled. Just warning. Let me see. Of course, you may need a calculator. Especially engineering calculator. But no program. Because some of the modern electronic calculators can have a mode, again, you can calculate the determinant. You just input numbers and you can get the output, right? So You just use the calculator for basic arithmetic operations: add, subtract, multiply, and division. Only for any questions? 우리 그 저기 옛날 퀴즈 어디 올라가 있나? 온라인 강의. Okay. So previous lecture notes and quiz problems, you will be able to find it in the electronic lecture room. We used to have a Google site, but somehow it disappeared. So this is about the time if you have any questions regarding quiz. It's going to be 1 hour, maybe 1.5 hours, depending on the number of problems. And the homework problems I gave you during the last week and previous week will be useful or helpful if you had time to solve some of them. So you are allowed to bring one cheating sheet, means you are going to be very busy. Because we don't what else? Actually, my favorite date for quiz is October 13th, Friday. My favorite date for quiz. But for the last 20 years, I didn't have that much luck. So I never had a class on a Friday. And October 13th, the Friday, you know why it is the best day for quiz, right? Maybe I will tell you about the history about October 13th, the Friday, why it is supposed to be the date for the bad luck. It all dates back to 1305. Maybe next time. So previously, we have covered the determinant, say A. So I'm going to just review some of the topics that we have done last week. A11, A12, 113, A21, A22, A23, A31, A32, A33. So in order to find the determinant A is defined as C11, A11, right? C12, A12. C13, A13. C11 is minus 1 to the 1 plus 1, M11. And M11 is a minor matrix that is actually the determinant of a matrix that is obtained by dilating the first row and first column, right? M11 is called a minor, and definition of a minor is determinant of a submatrix which is obtained by deleting the first row and first column. So that is a useful definition if you can remember that. So if you delete this and this, you have ended up with minus 1 to the 1 plus 1 is equal to 1, right? It's basically minus 1 to the 2, so it is 1. So A22, A23, A32, A33. So A22, A33 minus A23 minus A32. C12 is minus 1 to the 1 plus 2. M12 is minus 1 to the 1 plus 2 is minus 1 to the 3. That is minus 1, right? So minus of determinant which is obtained by first row and second column. Deleting the first row and second column, you get first this, right? So A221, A23, A31, A33, which is minus of A21, A33 minus A23, A31. C13, minus 1 to the 1 plus 3, M13. So by now you must be familiar with the definition or operation of how to obtain this M13. So it's the determinant of a submatrix obtained by deleting the first row and third column, right? So this is plus. Minus 1 to the 1 plus 3 is minus 1 to the 4, which is 1, right? And we delete the first row, third column. You ended up 2, 1, 2, 2, A31, A32. It's A21, A32 minus A22, A31. So determinant A is actually A11, A22, A33 minus A23. This is A32. One, A22, A33, right? And A23, A32, right? Minus A12, A21, A33 minus A23, A32, I think. 1, 2, 3, 3. 1, 2, 2, 2, 2, 2, 3. Oh, 3, 1. Sorry. 2, 3, 3, 3. Plus A13, A21, A32 minus A22, A31. And then actually it can be as computed as epsilon ijk a1i a2j a3k k. So maybe we can do some example. Let's say 1, 0, 2, 3, 4, 5, 6, 7, 8. Probably I have done that last week, but maybe we can do it again. So actually you can choose any column or any row. So one times determinant of 4, 5, 7, 8 plus 2 times 1 plus 3, 3, 4, 6, 7. $32 minus 35, right? Plus 2, 21 minus 24, which is minus 3, minus 6 is minus 9. How about the other method? Epsilon ijk is 1 minus 1, 0, right? I equal j equal k and even permutation. I equal j equal all different and the odd permutation otherwise. So let me check 1, 2, 3. Even permutation. We have epsilon 1, 2, 3, epsilon 2, 3, 1, epsilon 3, 1, 2, right? Odd is the other way around. 1, 3, 2, epsilon 3, 2, 1, epsilon 2, 1, 3. So this is plus 1. This is minus 1. So you can just write it down. Epsilon 1, 2, 3, A1, 1, A2, 2, A3, 3, plus epsilon 2, 3, 1, A2, 2, A1, 2, A2, 3, A3, 1, plus epsilon 3, 2, 1,
A13, A21, A32, plus now the odd permutation, epsilon 132, A11, A23, A32, plus epsilon 321, A13, A22, A31, plus epsilon 213, A12, A21, A23. So maybe we can move to this. Maybe we can divide some block. 2. So A11 is 1, right? The first one is, so even permutation, epsilon is plus 1, right? So A11 is 1, A22 is 4, A33 is 8, plus 231, A12, A12 is 0, right? A23 is 5, A31, 6, A32 is plus, A13 is 2, A21 is 3, A32 is 7. Now so we have minus sign because the odd permutation, the epsilon becomes minus 1, right? So minus 1 times A11 is again 1, A23 is 5, A32 is 7, A321 minus A13 is 2, 22 is 4, 31 is 6, minus A12 again 0, 21 is 3, 23, 33 is 8, this is 3. So let's check. 32 plus 42 minus 35 minus 48 equal to minus 9, right? So actually, two methods with the same answer. So actually, determinant, you can choose any rows. So, because I have shown that only for the 2 by 2 cases, but any size of matrix, I start with A11, C11, but you can start with A21, C12, something like that. So at least I have shown that these two methods are with each other, right? And so instead of 1, 0, 2, 3, 4, 5, 6, 7, 8, as a matter of fact, determinant can be expanded in any rows or columns. So determinant is actually A11, C11, A12, C12, A13, C13, but also you can use A21, C21, A22, C22, A23, C23, and etc. So to choose any rows or any columns with the largest number of zeros. So wisdom is you choose. So you can choose the rows or column with the largest number of zeros. So maybe you can try to find a different matrix. 1, 0, 2, 3, 4, 5, 6, 7, 8. I just interchanged the first two rows of the previous matrix. I just changed the rows and see what happens. So in this case, you can start with a C 2, 1 plus 2 times C 2, 3. So in this case, the sum matrix is -1 to the 1 plus 2 plus 1, M21 plus -1 to the 2 plus 3, twice over M23, right? So this is -1 to the 2 plus 1 is minus. So minus over matrix, which is obtained by deleting the second row and the first column, which is you delete the second row and first column. So this is 4, 5, 7, 8 times 2 times -1 to the 2 plus 3 is -1 to the 5, which is again -1. M23, you delete the second row and third column, you ended up with 3, 4, 6, 7. Minus over 32 minus 35 minus 2, 21 minus 24 is plus 9. So actually, you found that there is an interesting property. If we change the rows of a matrix, then determinant change the sign. Right? The only matrix from the previous matrix, the difference is you change the rows. First two rows, right? So I'm not going to prove it mathematically, which is going to take some time, but to state the fact that if you change any two rows or any two columns, then the determinants change the sign. If you change interchange, actually change the rows or columns of a given matrix, the determinant, the resulting determinant changes sign. This is a very useful fact that you need to maybe remember. I'm going to spend some time with the column matrix. N by 1 column matrix. Say x1, x2, xn. And I'm going to use a special notation to denote this one by column matrix X. And it's called cat vector. So this particular notation is actually different from majority of the engineering mathematics text, but will be very useful, this notation. Very useful if you are interested in quantum computing or quantum technology. So in quantum computing or in quantum technology, we use this particular notation very often to denote a particular state, or to compute. And this is sometimes called qubit. Anybody heard about qubit? Newspaper? No? Okay, good. Sometimes called qubit. But we are not going to cover that particular subject, but just use this pen notation to denote the column vector. N by 1 column vector. So some of you may have heard about quantum computing, right? 양자 computer? Or in French, it's ordinateur quantique. Oh, by the way, anybody who has not heard about complex numbers, raise your hand. Complex number. You never heard about complex number? Okay, so I'm going to cover some basics of complex numbers here. It's very important too, especially for the quantum computing. Okay. Beginning of this class, we have discussed numbers which is close to the 4 basic arithmetic operation, right? So the first number system that is close to the 4 basic operations, arithmetic operations are rational numbers, right? And there are some numbers which we use, like when you square, you have 2. That means we define square root of 2, right? I hope at least you know about this square root, right? So rational number plus those square root called irrational numbers. This is example of irrational number. So rational number plus irrational number forms real number. This is our number system. Around 17th century, some mathematics asked question: is there any number when you square gives -1? So as in the case of irrational numbers, the mathematician defined the new number as I, square root of -1. Let's try to find out who discovered this number. Let me check. Google might have. So according to the Wikipedia, I don't know. Let me see. By oh. 17th century, René Descartes. So he called this particular number imaginary number. Because suppose two numbers that gives -1 and you square it only exist in your mind, right? So the Descartes called it imaginary number, and z is x plus iy. X and y both belong to real number. It's called complex number. And actually, in the second semester, I'm going to cover complex variables, and we are going to show that this complex number also satisfies 4 basic arithmetic operations. But until then, you just believe that this number also satisfies the 4 basic arithmetic operations. Otherwise, I can show that it takes 2 hours. So let's just take it for granted. And complex conjugate is defined as x minus iy. Then z times z complex conjugate is x plus iy. X minus iy is called x squared plus iyx minus ixy plus I times minus I y squared. And this cancels each other. This becomes plus 1, right? Because I squared is minus 1, so minus I squared is supposed to be plus 1. So this is actually x squared plus y squared. And we sometimes call it the absolute value. Oh. Even though some of you may not have heard about complex numbers, I hope this gives the basic information, basic knowledge you can proceed. So let's say cat vectors and Z1, Z2, Zn all belongs to complex numbers. Set of we can define new vector, which is actually row vector. Complex conjugate, which is actually obtained by taking a transpose, right? The transpose operation changes column into row, right? Or row into column, vice versa. And take a complex conjugate. This operation is called adjoint operation. It's called dagger. The transpose and complex conjugate is called dagger, adjoint operation. And it has a name, bra vector. So why the other vector is called cat vector and this new vector is called bra vector has a historical meaning. But just be patient for a few more minutes. Then we can define with the bra vector and cat vector, we can define inner product. Say C, C. Z1 complex conjugate, Z2 complex conjugate, Zn complex conjugate, Z1, Z2, Zn. So this is basically just multiplication of row by column, right? So this is C1 complex C1, C2 complex conjugate to C2, blah, blah, blah. Cn complex conjugate to Cn. So Z1 square, Z2 square, Cn square. In English, what is this called? In English, what do you call this? Anybody? How about this? What do you call this?
Bracket?
Right, correct. Bracket. This is parenthesis. very good, bracket. So you cut it in half, right? You just cut. So left side is called bra, right side is called cat. In 1925, Paul Adrien Maurice Dirac, he actually used this terminology to denote a particular column vector and particular row vector as a bra vector and cat vector. He invented this notation and he got the Nobel Prize next year. Not because he invented this notation, but this is part of his work. I mean, his invention. So Dirac is one of the founders of quantum mechanics, and he's the one who introduced this notation. So sometimes called Dirac's notation, the bracket, or sometimes called Dirac. So let's start with, still need some time to copy. So today, basically we are going to learn a bunch of new notations. So you probably need to memorize the notations. So before I proceed, maybe I will continue the history of October the 13th. In 1305, the Pope, Joa, named Clement V, ordered the arrest of Templite all over the Europe. In October 13th, Friday. So that was the origin of the October 13th Friday, because many of the Templites was arrested and executed by that particular pope. There was a political struggle between the group backed by the Templite and by the Pope during the Crusade. Crusade is 십자군전쟁. The Templites actually control the money of all over Europe, and the Clement V wanted to control that money by arresting those. So that's the origin of some history. So it may not be directly related to the math, but useful knowledge, right? So maybe we can take a break for a few minutes and continue. So let's say we have two cat vectors, x1, xn. And we are assuming that those x's and y's are all complex numbers. Then x and y is defined as x1 complex conjugate, x2 complex conjugate, xn complex conjugate, y1, y2, yn. So x1 complex conjugate to y, y1, x2 complex conjugate to y2, etc., etc., xn complex conjugate, yn complex conjugate. If we interchange x and y, y1 complex conjugate x1, y2 complex conjugate x2, yn complex conjugate xn, which is actually x1, x1, y1 complex conjugate, n complex conjugate, x2, y2 complex conjugate, no. Sorry, I made a mistake. x1 complex conjugate to y1, a complex conjugate, x2 complex conjugate, y2 complex conjugate, because x complex conjugate is x, right? xn complex conjugate, yn complex conjugate, which is actually sum of the complex conjugate, x1, y1, x2, which is actually xy complex conjugate. So in inner product, if you change the order, you just put the complex conjugate in inner product. This cat vector satisfies very interesting properties too. Some properties cat vector. The collection of xn or x, maybe xn of vector space from V. So if property 1, if xi, xj belongs to V, then for any C1, C2, C1, X1, I, CI, CJ, CJ, XJ also belongs to vector space. It's called a vector space. Probably you have learned in your freshman calculus, right? So vector space is a set of cat vectors, and one of the properties is the sum of the cat vectors belongs to the same vector space. This is called a superposition. With inner product defined is called inner product space. Or sometimes called Hilbert space. So inner product space or vector Hilbert space is a particular vector space that with the inner product defined. But actually there is a small difference between inner product space and Hilbert space, but at this stage you don't have to worry about the small distinction. If some particular vector ei, ej called author normal feature other. Orthonormal to each other. Actually, author is a Greek word. Meaning perpendicular or straight. So there is a word called orthopedic. Orthopedic. Do you know what this orthopedic means? It's one of the typical toy words. It's a branch of medicine that stratifies your bone. 정형외과. Orthopedic. Straighten your bones. The doctor is called orthopedician. Orthopedician. Orthodontic. It's a branch of dentistry that straightens your teeth. 치열 교정, right? Or orthodontist, person dentist, someone who straightens your teeth. 치열 교정사, right? But actually, it's a part of dentist. Part of the work for the dentist. Orthopedic. There is a particular name that why we call orthopedic. Usually children are easy to have their bones broken, right? So pedic is usually related to the children, the pediatrics. Is a branch of mathematician that specializes in the care of children. And doctor, pediatrician. So if you know the origin, like Greek or Latin, then it is relatively easier to associate with the English words. Because I think about 70% of the English words came from either Latin or Greek, origin. Actually, majority of English words came from French. In the year 1065, that the Norman conquered England, and then they conquered for several hundred years. So the original English became like a Scottish and Irish, and the remains combined with the French and become a modern English. But the French also contains a lot of Latin and Greek. Why I was doing this? Okay, I was explaining orthonormal. Orthonormal means perpendicular to each other. So orthonormal means two straight lines meet, and that's perpendicular. But you can learn some English word. There's a fringe benefit. For example, for two-dimensional vector space, let's say we have E1 and E2, and see what happens. So what is the inner product with E1, E2? Root square root of 2 1, 1, square root of 2, 1 minus 1, right? So 1 over 2. What do we have? 1 minus 1 is equal to 0, right? How about the other way around? E2, E1 is actually supposed to be E1, E2 complex conjugate, right? If we interchange the order, then we just put complex conjugate, again 0, right? How about E1, E1? Equal to 1, right? How about E2, E2? Again, 1. So those are the typical example of a vector which are orthogonal to each other. So if we have if EI, EJ, Kronecker delta. So we learned that last week, right? That means when I and j are the same, it is equal to 1. When they are different, it is 0. Then this particular set is called orthonormal basis. N-dimensional vector space. So for two-dimensional vector space, we can also different vectors. Say E1, 1I, E2, 1 minus I. And you see what happens if they can also form vector spaces. Maybe I can call tilde to distinguish the one from the other one. Let's say E1 tilde E1. Root 1 over square root of 2, 1 minus I, right? Square root of 2, 1 I. So it becomes 1/2 1 minus I square, right? Is equal to 1. How about E2? Tilde. It has a name called tilde. One I, 1 minus I, one minus I square is again 1, right? How about E1, E2? Square root of 1, 1 minus I, square root of 2, 1 minus I is equal to 1 over 2. Actually, this must be 1 over 2. 1 minus I square plus I square, right? Is equal to 0. E2 tilde E1 is actually supposed to be E1 tilde E2 tilde complex conjugate, and again 0. So this E1 and E2 are also orthogonal to each other, right? It's the orthogonal basis for two-dimensional vector space. So that means the orthogonal basis cannot be unique. It can have different forms. It doesn't have to be unique. Another obvious case. Say E1 prime, 1, 0, E2 prime, 0, 1. This is obvious, right? E1 prime is just 1, right? E2 prime is equal to 1. E1 prime, E2 prime is equal to 0. E2 prime, E1 prime. So that means E1 prime, E2 prime is also on orthogonal basis. There is another interesting property, product called outer product. It is defined as this way, x, y. Simply this way, x1, 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 yn, xn, y1 complex conjugate, xn, y2 complex conjugate, xn, yn complex conjugate. And interchange the order, there is no relation. So in general, different. The outer product has interesting properties. Very simple rule. So just keep the y whole row, but each element is multiplied by x1. x1, x1, x1. And through is multiplied by xn. And we usually make out the product with the orthonormal basis. So maybe you need time to digest. So I will practice with the 2x2 cases mostly. Can I move on? So we have this particular basis, right? What is this E1, E1? Right? Times root 2, 1, 1. So by the definition, 1 over 2, 1, 1, 1, 1, right? How about E2? One minus 1, 1 minus 1, right? So square root 1 over 2, 1 minus 1 minus 1, 1, right? If we add them together, what happens? Two, right? Identity. Right? The outer product, some of the outer product of bases is becoming identity matrix. Let's see what happens to the other bases. I introduced 3 different bases, right? So let's see what happens. It's a very simple matrix, but I think actually you can learn a lot from very simple examples. How about in this case, tilde matrix, right? E1 tilde was defined as square root of 1i. E2 tilde was defined as 1 over square root of 2, 1 minus I. And let's see what happens. So outer product, E1 tilde, right? So square root of 2, 1i, square root of 2, 1 minus I, right? When you make a bra vector, you just take a transpose and complex conjugate. So it becomes 1 over 2, 1 minus I, and I times minus I is equal to 1, right? How about E2 tilde, E2 tilde? Square root of 2, 1 minus I, square root of 2, in this case 1 plus I. It becomes 1 half, 1i minus I, 1. So if we add them together, what happens? E1 tilde, E1 tilde, E2 tilde, E2 tilde is 1/2, 1 minus I1 plus 1, 2, 1I minus I1, 1/2. It's 2, 0, 0, 2, right? And it's 1, 0, 0, 1, identity. Even though the form of the orthogonal basis was different, but the outer product of the sum of them become identity. How about third basis? Third basis was, maybe you need time to copy. Do you think I'm going too fast? It's okay? Some of you might be curious because I usually bring only one, just pencil and iPad, right? No note. So, because I have been teaching this class for over 20 years, everything is in my brain. Yeah. How about the third cases? Third case. E1 prime, E2 prime, where E1 prime was 1, 0, E2 prime was 0, 1. That's easy. E1 prime, E1 prime, 1, 0, 0, 1, 0, right? So this is 1, 0, 0, 0. E2 prime, E2 prime, 0, 1, 0, 1, 0, 0, 0, 1. So E1 prime, E1 prime, E2 prime, E2 prime is simply just 1, 0, 0, 1 is identity. So it doesn't really matter which kind of form that particular basis take. As long as you just sum the product out, sum of the outer product of each basis, it becomes identity. So it's generally true. So if n-dimensional vector space, then E1, E1, E2, E2, En. In general, for any n-dimensional, we have n. This is called the completeness property of orthogonal basis. So the orthogonal basis satisfies very interesting outer product property. This is called completeness. And will be very useful in the future. Say A n by n matrix. When adjoint of A is same as A, it is called self-adjoint. A is called or Hermitian. So A, what is A adjoint? 1, 3, 2, 4, right? In this case, A and adjoint are not the same, right? When A is called 0, 1, 1, 0, then A adjoint is again 0, 1, 1, 0, right? So in this case, A is adjoint. And A example. Zero minus I 0. What is adjoint? You take a transpose and complex conjugate. So you take transpose, 0 I minus I 0, and you take complex conjugate. 0 minus I 0, again A, right? So this particular example is Hermitian. A is 1, 0, 0, minus 1. It's obviously Hermitian, right? So this particular matrix is called Pauli matrix. As a name. Matrix is actually plural. The matrices. Pauli matrices. These Pauli matrices are very important in quantum computing as well. But so I'm going to state one very interesting property of this Hermitian matrix. So can I move on? So this topic is really important. So maybe I can ask you in the quiz. A is a Hermitian matrix. One. Just real numbers. Lambda I also normal basis. So actually I have to write down this way. Lambda 1, lambda n, E1, En, such that A, EI, so when A is a Hermitian matrix, then it has the following properties: that there exists a real set of real numbers, lambda I, and also normal basis, E1, 2, 3, such that this particular property is satisfied I. That second property is already, I showed that for 2 by 2, right? But third property is really interesting part. A can be represented by the sum of lambda I this is called the spectral theorem. So this statement is really important. It's called the spectral theorem. It's related to the Hermitian matrix. So when A is a Hermitian matrix, it says following properties: that number one, there is a set of real numbers, lambda I, and also on normal basis, such that A times EI is equal to lambda I times EI. Secondly, outer product of the orthonormal basis is I. That has been shown already, right? So you accept this property. Third property is this matrix can be represented by the sum of the outer product weighted by a particular number. And this whole thing is called spectral theorem. It's probably one of the most important theorem in linear algebra. And you are just learning in compact form. Usually, if we have one semester linear algebra class, the spectral theorem actually comes towards the end. So you need at least one semester of linear algebra to cover that. But I'm just going to like a quick course, accelerate the speed. You just need to observe the basic idea. So let's show this theorem by considering special cases. So case 1, when A is 0, 1, 1, 0. Actually, it has, sometimes you rewrite this as sigma x. Sometimes write as x, depending on. This is a quantum computing notation. Consider the basis E1. let's check if A times E1 is what? 0, 1, 1, 0, square root of 1, 1, right? It becomes square root of 1, right? 1. E1. Or AE2. One minus one. What happens? This becomes minus one. This becomes 1 minus E2, right? So in this case, we have lambda 1 is plus 1, lambda 2 is minus 1. Let's see if the second property, the last property satisfies the spectral theorem part. It's only 2 by 2, so very simple, but it contains all the basic concepts of the spectral theorem. This was your A, and to see lambda 1 E1 E1 plus lambda 2 E2 E2. Plus 1, square root of 2, 1, 1, square root of 2, 1, 1, right? Plus minus 1, square root of 2, 1 minus 1, square root of 2, 1 minus 1. One over 2, 1, 1, 1, 1, right? Minus 1 over 2, 1 minus 1, minus 1, 1. What do we have? 1 over 2, 0, 2, 2, 0, right? 0, 1, 1, 0, which is A, right? I mean, if you check, you can check. You ended up A, right? This. So this property gives A. Maybe another case. I think 2, 3 cases will be enough to convince you about the spectral theorem, right? So, case 2. A is called 0 minus I 0. And of course, sometimes it's called sigma y. Y. This is again quantum computing notation. And consider E1 tilde. 1I, E2 tilde. we already know that this E1 tilde and E2 tilde are orthonormal bases, and the some of the outer products satisfy identity, right? I have shown that before, about maybe 20 minutes ago. Check with A, E1. 0 minus I, 0. Square root of 2. This and this. 1, right? This and this. I. E1 tilde, right? How about A, E2? 0 minus I, 0. 1 minus I. This and this. Minus 1. This and this. I. That is minus over E2. Right. So again, we have lambda 1 is equal to 1. Lambda 2 is minus 1. And let's check if lambda 1 E1 tilde plus lambda 2 E2 tilde is square root of 2, 1I, 1 minus I, minus square root of 2, 1 minus I, 1I. Over square root of 2, square root of 2, so 1/2. 1 minus I, 1 minus 1 over 2, 1 I minus I, 1. So it becomes 0 minus I, 0, right? Which is A. So this property is true for second cases, right? I can go one more time. The third time is perfect, so I think some of you are still copying, so. Case 3. When A is 1, 0, 0, minus 1, which is sometimes called sigma z. Of course, this is again quantum computing notation. Let's say E1 prime, 1, 0, E2 prime, 0, 1. And A times E1 prime is 1, 0, 0, minus 1, 1, 0. Again, 1, 0, right? A times E to the prime, 0, minus 1, minus of E2. So again, lambda 1 is plus 1, lambda 2 is minus 1, right? So property 1 is satisfied always. And property 2, we have seen that the sum of the outer product is always identity, right? How about this? Lambda 1, E1 prime, lambda 2, E2 prime, E2 prime. 1, 0, 1, 0, minus 0, 1, 0, 1. It's obviously 1, 0, 0, minus 1. So again, A. So Hermitian matrix, we have a spectral theorem that satisfies A. So we, then we have a very interesting property, such as, so in general, A En, En, right? How about A square? En, En times M, lambda M, Em, Em, which is Nm, lambda N, lambda M, En, 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 En. How about, but this is what? This is called En, Em, Kronecker delta Nm, right? And N and M are different, they are 0, otherwise 1. So we have a summation of N and M, but actually at the end of the day, we just need sum over N. So it just becomes sum over N, lambda N square, En, En. And then you can go on. A to the K, sum over N, lambda N to the K, En, En. So, assuming that I can ask you a very wicked question. Say this page, the A to the K is each numbers to the K with that particular outer product, right? So A 0, I, minus I 0. What is A 100? Of course, you can do that, right? You can multiply 100 times. How long will it take? You can do it, right? You can multiply 100 times. Each time may take 1 minute, so 100 times 100 minutes, hour and a half. So it's perfect speed when you are on the blind date, right? But actually, if we know the spectral theorem is simply minus 1 to the 100 times E1, E1, minus 1 to the 100 times E1, E2, E2, right? I mean, if you take a look at from the, you borrow the result from the, use this. What is minus 1 to the 100? 1, right? So this is E1, E1, plus, what is minus 1 to the 100? Again 1, right? E2, E2. So we know the answer without actually multiplying this matrix 100 times. But I will give homework. Do it by multiplying A 100 times. Okay? Hour and a half. You can do it at home and see what happens. I think if you don't make any mistake, you will get identity. How about A101? Again, it's minus 1 to the 101, and plus 1. The first one is plus, not minus. To the E1, E1, minus 1 to the 101, E2, E2. So plus 1 to the 101 is still 1, right? Minus 1 to the 101, minus. You know this is answer A, right? So 100 times, actually, you can do it. How about million times? A to the million. Maybe. Okay, single calculation take 1 minute. Then million times is a million minutes, right? What is a million minutes? 1 hour is 50 minutes, right? So just simply, for the sake of mathematical calculation, let's assume that 1 hour is 100 minutes. Then 1 million minutes is 10,000 hours, right? So how many hours compose the day? 24 hours, right? Let's say 10 hours. Then 10,000 hours means 1,000 days, right? So 1,000 days is almost 3 years. So if I ask you homework to calculate this matrix times million times, it will take 3 years for you to compute, right? But if you know the spectral theorem, it's simply plus 1 to the million plus minus 1 to the million. And you know that what is plus 1 to the million? It doesn't matter, just 1, right? How about minus 1 to the million? Still 1. As long as the power is even number, it's always 1. So this is 1 plus 1, right? So this is E1, E1 plus E2, E2 is identity. So you can save 3 years of your precious time if you know the spectral theorem. How about 8 to the 1,000,003? you just need 3 more multiplication after 1 million, right? So plus a little over 3 years. But since you already know the spectral theorem, we know the answer, right? Plus 1 to the 1 million 3 to the E1, plus minus 1 to the 1 million 3, E2. So what is 1 to the plus 1 to the 1 million 3? It's plus 1, right? How about minus 1 to the 1 million 3? Minus 1. So it is simply E1 minus E2, which is A, right? Because you know the spectral theorem. So if you know some particular properties, your math could be fun and save a lot of time. Maybe I can stop here today? What do you think? I can cover some more material if you like. Or you can stop. No answer? You don't have any idea? Okay. Let's conclude this today's class. So spectral theorem can save a lot of your time, maybe 3 years. So if you don't know the spectral theorem and I ask you to this is homework, you will be doing the calculations for another 3 years, right? But you can do it in 1 minute here. So see you next week.